Hey everyone, Mr. Fransky here. Today we're going to be talking about U substitution, which is a method for evaluating indefinite integrals or antiderivatives with some expressions that are getting a little bit more complicated than what we've been looking at so far. We're going to start with some things that we know how to do already. So we're just trying to evaluate these indefinite integrals. Remember, that just means you're looking for the antiderivative, and of course we're looking for a family of functions here. You know what that means. So if you want to give this a shot, pause the video, do these real quick. I'll be with you in a sec. All right, let's give this a shot. So the first one we have e to the 2x. So we're looking for something whose derivative just leaves us with e to the 2x. Remember that e to the x is its own derivative, so we're definitely going to have an e to the 2x involved here. But when you take the derivative of e to the 2x, what's the problem? Take the derivative of e to the 2x, and you get e to the 2x, but you have to chain, so it'd be multiplied by 2. So we'd have e to the 2x times 2. We don't want that times 2, so how do we get rid of it? Well, initially, why don't we just put it over 2? Now when you take the derivative of this, you get e to the 2x times 2, and the 2's will cancel. Remember, you don't have to use quotient rule because it's just a constant. And of course, I'm sure you all remembered your plus c. Because now it could be any function that has this derivative e to the 2x. Yep, that's what we're looking for there. All right, next up, we got 3 secant x tan x. I can pull that 3 out to the front and just consider it later. Secant tangent is the derivative of secant. So this is going to be 3 secant x plus c. That's it. Next up, we got e to the x squared times 2x. So what's been happening here is they've already done chain rule, right? So if I just do the derivative, this is going to have an e to the x squared in it because the derivative of e to the x squared is e to the x squared itself. But then you would chain by multiplying by 2x. That part's right there. So it's just e to the x squared plus c. Take the derivative of this. Sometimes it seems kind of backwards. Like, how do you know this is the answer? And then you have to later check it. Lots of practice, right? Derivative of e to the x squared is e to the x squared times 2x because of the chain rule. Next up, we got negative 2x over x squared plus 1. This one's a little bit sneaky. So 2x is the derivative of x squared. And the way I look at this is we have a denominator of x squared plus 1 here. The way that things get in the denominator is often by doing the derivative of natural log, right? The derivative of natural log x is 1 over x plus c. Well, yeah, sure, let's do it like that. I shouldn't put plus c there. The derivative of natural log x is just 1 over x, right? So, yeah, because not plus c. What am I doing? So over here, if I think about this, if I do natural log of x squared plus 1, the derivative would be 1 over x squared plus 1. Then you have to chain, so you'd have a 2x hanging around. It's right up on the top. To make it negative, throw a negative right there, and then plus c. Because of log rules, you could throw this guy up to the top here. You could do natural log of 1 over x squared plus 1. Sometimes you'll see AP do stuff like this. We'll try to trip you up a little bit, right? And we know our antiderivative for for 1 over x is natural log of absolute value of x. So we should have some absolutes around this guy and some absolutes around this guy. Yeah, cool. All right, so just some kind of typical antiderivatives that we've seen already. So now we're going to learn about what U substitution is. This is kind of unchaining, and it requires less thinking. So we did this antiderivative by just thinking about it. We were like, well, e to the x squared, then you chain it, you get a 2x. What you do for U substitution is we say, well, we're going to change something in here to a U where we already see the derivative in the integrand as well. I'll show you what I mean. So in this case, what I'm going to do, just follow along with me now, and I'll kind of explain it a little bit on the back end. So we have, if we do U equals x squared, if we do U equals x squared, then du dx is going to be equal to 2x. Right? So if I say u is x squared, then du dx is 2x. Now what I'm going to do is I'm going to take these things, I'm going to substitute into my integral with them. So we have the integral, x squared is just u, so I'm just going to put a u there. And then du dx is 2x. This 2x right here is going to get swallowed up. That means that du is equal to 2x dx. Well, I have 2x dx right here. So I'm just going to replace it with a du. So we have e to the u du. Well, what is the antiderivative of e to the u? It's just e to the u. See? Less thinking. So e to the u plus c, of course. And then I'm going to substitute back in with the x squared. So this is e to the x squared plus c. Notice we got the exact same answer. We got e to the x squared plus c. And some of you might be out there saying, yeah, I could have done that without having to do this whole u thing. I can just look at it and think about it. I agree. We're going to get to somewhere it's going to be more complicated. I want to start with something that wasn't too bad. So let me take you through this again. How did I choose my u? I chose u because the derivative of x squared is 2x. I see that in my integrand. So I'm like, well, if I make u x squared, then du is going to involve a 2x. It's just going to get rid of that. It makes my e function a lot simpler to deal with, right? It just turns into e to the u. So what you have to do is you have to get u's in your integrand and then also change your dx to a du somehow. And it's going to involve kind of having a number stuck to it. So what's our method here? choose u so that du dx, at least the variable part, so we see du dx is 2x, is in the integrand. Multiplied constants can be handled. I'll talk about that a little bit later. So like if there was a 4 in the front here, I would still do exactly the same thing, right? Multiplied constants you can just pull out and deal with them later. Don't worry about it. Also, if this was like just x instead, which is what we're going to look at right now, we're still going to be able to deal with that x. So let's take a look at this. So e to the x squared 2x dx. This is the one that we just did, right? So we would say u equals x squared because the derivative du is going to be equal to 2x dx. Notice I just kind of skipped the du dx equals 2x. I just moved the dx right away because I'm looking to get rid of this 2x dx. So then I just substitute in. So we have antiderivative e to the u du, which is e to the u plus c. And then one common mistake that people make is they leave u's in their answer. Don't ever leave a u in your answer, right? Because there were no u's in the initial problem. You created this u, so you have to change it back to e to the x squared plus c. And that's our final answer. Okay. So now I talked about this multiplied constants. Multiplied constants can be handled. What that means is here, I have e to the x squared times x dx. I'm still going to use u equals x squared. We're going to talk about in the next slide about how to kind of choose your u values. Du then is 2x dx. You say, wait, there's no 2. I need a 2 here to be able to make this substitution. Okay, put one there. If you put a 2 here, I can't just put a 2. I also have to balance it out. So what I'm going to do is I'm going to multiply by 1/2 on the outside. I haven't changed anything now, right? I've basically multiplied by 2 over 2. Sometimes you'll see teachers do this. They'll say, put a 2 over 2 in front of it, e to the x squared x dx, and then pull this 2 inside. I think that's excessive. I think you can just do this. I trust you to put the 2 there. Just don't forget to put the 1/2 here at the same time. So now what we have is we have 1/2. So we have 1/2 integral e to the u, and now I have my 2x dx. I needed a 2 there because that's what du is. So we have e to the u dx. Well, du, excuse me. So that's 1/2.
If you're in the building, please come to the main office.
So that's 1/2 times e to the u plus c. Yeah, I'm going nuts. Okay, so 1/2 e to the u plus c, which is 1/2 e to the x squared plus c. There it is. So one reminder. Oh, I don't have it here. No, it's on the next slide, I guess. So remember, can't leave u's in your answer, so make sure you don't leave it like this. Make sure you get that 1/2 e to the x squared plus c. Sorry about that announcement getting in there. All right, moving on. So let's do some examples, some more examples. So here we have integral x squared plus x minus 3 times 2x plus 1. So I'm looking for here is a u where the derivative is also present. Okay, so I think a good choice. You always, on the next slide, we're going to talk about how to find these things, but I'm looking for something probably inside parentheses that has its derivative also present. 2x plus 1 doesn't look good because the derivative would just be 2. But what if I make this whole polynomial my u? Then u would be x squared plus x minus 3. And then du, well, it's the derivative of this guy. It's 2x plus 1 dx. Okay, so 2x plus 1 dx, hey, look, I have that right here. So this turns into integral u du. Okay, so I want to take as much out as possible. I could have just done x squared plus x, right? And the derivative du still would have been the same thing. It would have been 2x plus 1 dx, but then I would have had a minus 3 stuck on here. I don't want that. Make it as big as you can, because then if the constant disappears, it makes your life a lot easier. So antiderivative of u du is just u squared over 2 plus c. And now we substitute back in. So it's going to be x squared plus x minus 3 squared over 2 plus c. Always a good idea to check your answer. When you take the derivative of this, you take care of the outside function first. The 2 would come to the front and cancel, reduce down to 1. Then you'd multiply by the derivative of the baby function on the inside here, which is 2x plus 1. That's all there is to it. All right, next one we got root sine x times cosine x. So some people think that you could use either sine or cosine here. I definitely want to use sine x. The reason is because then du is just cosine x dx. Right, the derivative of sine x is cosine x. And also now I don't have to deal with the root. So some common mistakes people make. Sometimes people say that u is the square root of sine x. Okay, but then your du, you're going to have to chain on this. It'd be 1/2 sine x to the negative 1/2 times cosine x. I don't have this here, right? I don't have the 1/2 and the negative 1/2. That's not going to work well. But if I just do u equals sine x, then I have my du right next door in cosine x. And now all I have is antiderivative square root of u du, right? Because I have my du here, cosine x dx, and I have root sine x is just by root u. This is antiderivative of u to the 1/2 du, which is u to the 3/2 over 3/2 plus c. Also write that as 2/3 u to the 3/2 plus c. Put it back into x land, and we get 2/3 sine x to the 3/2 plus c. Is it here? Yes. Don't leave any u's in your answers, right? Got to go back to x's. The original problem had x's. Your final answer should have x's. Always not a bad idea to check your work. To check your work, if you want to check, just derive your final answer. So derive final answer. So like this last one, we could check. If we take the derivative, the 3/2 comes to the front, cancels with the 2/3, becomes a 1/2 up here. So we have the square root of sine x. Then we chain by multiplying by cosine x, and the constant disappears. Cool. So what to look for when you're choosing your u value? A few things here that you can kind of look at when you're choosing your u, and I think I have one more thing to add as well. Something inside of square roots, and don't include the root. So if you have like the square root of x cubed minus 3x squared plus 5x minus 4, great choice for u is that whole thing in there. Okay, that's what I would choose for u. Then you would end up just with root u, and hopefully you would have the 3x squared minus 6x plus 5 multiplied next door so that you could use that for u substitution. Because square root of u is easy to integrate, right? If you include the root, then you have to deal with the 1/2 coming to the front, the negative coming up to the top. It's way too much more than you want to deal with. So I just choose u's that are underneath roots. Another good choice, denominators. If you have like 1 over 3x minus 4, you do u equals 3x minus 4, then du is just 3 dx. You can create a 3, right? If you have integral of who cares what, put a 3 in here, put a 1/3 out here, you got your 3 dx right away. Not that bad. And then you just have 1 over u du. And that's just natural log absolute u, right? So denominators are really good. Under roots are really good. What do we got next? Inside trig expressions. Sine of 2x plus 1. 2x plus 1, great choice for u. Then you just have sine of u, really easy to integrate. Okay, you might have like sine of x squared. If that's the case, you better have a 2x sitting next to it because that's the chain part. That's your du would be the 2x dx. So really nice if you have any kind of trig that you can use that part on the inside of the trig expression. Inside parentheses in general, right? We talked about that before. If you have a few parentheses things, if you use one of them, hopefully the other one is the derivative of the first, because then chain rule has been done. But inside parentheses, good choice for u, and then all you have left is just u. Yep. Powers inside of powers. This is a tricky one. So in general, this is the one I was going to add, is just exponents in general. Even on the example we already did, a couple slides back, well, I have to go back too far. We had one that was e to the x squared. X squared was a good choice for u. Right? Then I just ended up with e to the u, antiderivative, that's just e to the u. But powers inside of powers. So if you have something like antiderivative, let's say, let's see here, x times the square root of, let's do x to the, let's do the 4th. Cube root of x to the 4th. Let's do it like that. Yeah, dx. Okay. So something like this. This is something we haven't seen yet. It's pretty tricky. But what I would say is a lot of people would be tempted to say u equals x to the 4th. Well, if u is x to the 4th, then du would be 4x cubed dx. I don't have an x cubed, and I can't create it. You can't create x's. I couldn't multiply by x squared here and divide by x squared on the outside. It doesn't work because if there's an x here, that would have to be pulled inside the integral. I would have to integrate it with the rest of it. But x by itself is the derivative of what kind of a thing? I think that's the derivative of a quadratic. So what if I did u equals x squared? Then du would be 2x dx. So just follow with me for a second here. You might not see where this is going, but if u is x squared, then du is 2x dx. I have x dx. I need a 2, so I'd throw a 1/2 out front. So 2x dx turns into my du. So I have 1/2 integral something du. Now the trouble is this x to the 4th. Well, what is x to the 4th in relation to x squared? That is, so x to the 4th is x squared squared again, right? So what I have here is the cube root of u squared. That's u, so we have 1/2 integral u to the 2/3 du. That'd be 1/2. U to the 2/3 plus 1 is u to the 5/3 divided by 5/3 plus c. And then change back to x's. So u is x squared, so I'd have 1/2 x squared to the 5/3 times 3/5 or over 5/3. I'll just leave it, and then plus c. So, like I said, kind of tricky if you have powers inside of powers. But in general, exponents, if you have an x in the exponent, good choice for you. But these powers inside of powers can be a little bit tricky to find. But just look at the degree that you have for the stuff outside and say, I need that to be the derivative. So then I just have to go up one power to make the exponent work out. All right, so let's try some more examples. So we're going to kind of use that idea that we were just talking about looking for u for some of these. If you want to try any of these on your own, please feel free. Otherwise, feel free to work them with me. So we got cosine of 5x dx. I think u equals 5x is a great choice. You can probably do this one in your head, but u substitution just takes all the guesswork out of it. So if u is 5x, then du is 5 dx. I don't have a 5, but I can make one. Throw it right here. Then what else do I need? I need a 1/5 on the front. Now I haven't changed anything. So we have 1/5 integral cosine u du, right? Because the 5 dx turned into a du. That is 1/5 cosine u plus c, or sorry, sine u, because I'm anti-deriving. So sine u plus c, which is 1/5 sine of 5x plus c. You want to check your work, take the derivative, cosine 5x, chain times 5, 5's cancel. Over here we got cosine x to the 5th, x to the 4th. Same deal. I'm going to use u equals x to the 5th because it's inside of my trig function. Then du is 5x to the 4th. I have the x to the 4th. I need the 5. So I need a 1/5 out here. So we have 1/5 integral cosine u du, because 5x to the 4th dx is my du. And then antiderivative cosine, we have 1/5 sine of u plus c. The reason I hesitated there is because sometimes I go straight into x at that point, but I want to be methodical with you guys. So we got 1/5 sine of u is x to the 5th plus c. Check the derivative. Take the derivative of this. You'd have 1/5 cosine x to the 5th times 5x to the 4th. There's our x to the 4th, and the 5's cancel. Next up, I'm going to use our denominator here. I think I'm going to leave the cube out of it. If I did so I'm going to do u equals x squared plus 2. If I did x squared plus 2 cubed, when I took the derivative, the 3 would come to the front. I have to chain. I don't have any of that stuff, so I'm not going to deal with that. So if u is x squared plus 2, then du is 2x dx, because the 2 disappears. Notice some people might just be tempted to do x squared, but you want to do the whole thing, x squared plus 2, because that makes the 2 disappear. I have the x, I need a 2. I forgot a dx on this, my bad. So I need a 2, so I need a 1/2 in the front then, because I can't just multiply by 2 out of thin air. So I have 1/2 integral 2x dx, that's my du. So I'd have du over u cubed. Some people have been asking me, what does it mean when the du is on the top? I just slid it up. Right? You could do 1 over u cubed du. AP sometimes will do this. They'll throw du on the top instead of writing it next door. It's the same thing, though. So this is 1/2 integral u to the negative 3 du, which is going to be 1/2 u to the negative 2 over negative 2, right? We add 1 and divide by the same thing, plus c, which is 1/2, let's see, what's u? U is x squared plus 2. So we have x squared plus 2 to the negative 2nd divided by negative 2 plus c. Let's see if we can do better. So this is going to be negative 1 over 2 times 2 is 4, x squared plus 2 squared plus c. You can try that derivative on your own. That's going to be a little bit more involved one, right? Bring that negative up. It's going to come to the front, cancel with the bottom. That should be a negative. I covered it with my box. And then you'd be chaining times 2x, and the 2 would cancel with the other 2 that's left over. Yep, works for me. Next up, good choice for you here is 3x minus 11. So then du is 3 dx. So we need that 3. Let's put it here, because I'm getting out of room over there, 1/3 here. So the 3 dx turns into a du. I have 1/3 integral square root of u du, which should be 1/3 u to the 1/2. So it's u to the 3/2 divided by 3/2 plus c. So multiply by the reciprocal here. We have 2/9 times u is 3x minus 11 to the 3/2 plus c. Cool. All right, you're getting indefinites now? A couple more examples. So this guy, I wonder if there's supposed to be an x in there. I might have written the problem down wrong. Let me take a quick look. Yes, there's supposed to be an x in here. My bad. Okay, so we have x secant x squared tan x squared dx. The reason I know that is because if we make the u x squared, then du is 2x dx. I can't fabricate an x. There had to be an x there to make this work. So now I need a 2. I need a 1/2 in the front. So 2x dx is my du. I have 1/2 integral secant u times tan u du. This is 1/2 secant u plus c. right? Because derivative of secant is secant tangent. U is x squared, so that is 1/2 secant x squared plus c. Double check. Derivative would be 1/2 secant x squared tangent x squared. There it is. Times 2x. The 2's would cancel, and the x would stick around. And if I'd written the problem right, it would have been there. This is an interesting one. If you want to try it on your own, you can. The u value here, I'm going to use the bottom square root. I'm not going to have the square root as part of it, because then my du would be complicated. So you have x squared minus 3x plus 2. Then du is 2x minus 3. You say, wait, there isn't a 2x minus 3. What can we do with this top, though? We can take out a 2. So we have 2 integral 2x minus 3 over square root x squared minus 3x plus 2 dx. So now we have our 2x minus 3. So this is 2 integral. So this part turns into my du. So we have du over square root of u, and that's it. I just feel like there should be a du at the end, but if they write it on the top, you don't have to have it. So let's see, this is 2 integral u to the negative 1/2 du, which is 2 times, add 1 to this, is u to the 1/2 divided by 1/2 d plus c. Multiply by the reciprocal here, we have 4 square root of u, which is x squared minus 3x plus 2 plus c. Take the derivative of that and double check that it equals your integrand, but that should work out just great. What else? Definite integrals, fine. Finally, all right, so we're integrating from 2 to 4, 2x minus, dx over 2x minus 3. So here's what you want to do with a problem like this. When we're integrating with x values, I call this x land. Okay, and what we're going to do is we're going to go over to u land. So we change this. I'm going to do u equals 2x minus 3. And then du is 2 dx. So we need a 2 here. We need a 1/2 in the front. So now we're integrating 1/2 integral of 2 dx turns into du. So we have du over u. Here's the tricky thing. These limits, if you think about this function, I'm going to graph this on a calculator in a second, I'll show you, but 1 over 2x minus 3, that would have an asymptote at positive 3/2, 1.5, like that, and it would kind of look like a 1 over x parent function. Integrating that from 2 to 4, right here to here, if we change it to just 1 over x, it's like 1 over u, technically, that looks like this. Integrating that thing from 1 to 4, or 2 to 4, is going to be very different. It's going to be much smaller than this integral from 1 to 4, because this guy's getting more meat under it before it's decreased so much. This is going to be different. The limits change. So all you do is you put these into the u function. So I do u of 2, which would be, I just plugged it into the u function. 2 times 2 minus 3. And I do u of 4, which would be 2 times 4 minus 3. 4 minus 3 is 1. 8 minus 3 is 5. So now what I do is just integrate in what I call u land. Okay, so we integrate from 1 to 5. This integral from 1 to 5 should be exactly the same as this integral from 2 to 4. And that's what we're going to show in the calculator in a second. So now what I do is I do 1/2. Antiderivative of 1 over u is natural log absolute u, excuse me, evaluated from u equals 1 to u equals 5. I like to write the u's to remind myself that they're u values, not x values. So what does that turn out to be? 1/2 ln of 5 minus ln of 1. ln of 1 is 0, so this is 1/2 ln 5. And I crunched this before. I think it's like 0.8 something. We'll check it on the calculator. I don't remember what it is, but you can just leave it like this. 1/2 ln 5 was no calculator. If it was a calculator, you could actually plug it into your calculator and figure it out. There's another option to do this. You could leave it in x's. So at this point, you could have 1/2 ln absolute u evaluated from x equals 2 to x equals 4. And then what you would do is you would change this to 1/2 ln. You would change the u back. So you'd have absolute 2x minus 3 evaluated from x equals 2 to x equals 4. But what's the first thing that happens when you plug 4 into this? You plug 4 into this, you get 8 minus 3, it's ln of 5. Then you plug 2 into this, you get 4 minus 3 is ln of 1. You end up with exactly the same thing that we had before, but it just took you more work and more thinking to get to it. I prefer to change everything over to u's. There are some problems where they actually force you to change to u's on AP. They just say, which of the following is an equivalent substitution or something, and you have to make sure that the limits are changed because they've changed it to u. So it's just something to be careful of and just watch out for, because I think changing your values to u's is a lot better. So let's go over to a calculator and see how this actually looks. Keep. Come on. This guy. Okay, so this right here that I have graphed is 1 over 2x minus 3. So I'm going to go to Menu, Analyze Graph, and I'm going to integrate. Number 7. And we're integrating, I believe it was from 2 to 4. Okay, and we get a value of 0.804719. And now the other one, I'm going to graph, let's see, we have 1/2 integral from 1 to 5, 1 over u du. I'm going to pull the 1/2 in, so it's just the integral from 1 to 5 of 1 over 2u du. I think I have it up here already. Yeah, so we have the 1/2, and we also have the 1 over x in there. And so I'm going to check that box so that it actually graphs it. Now we should be able to, what should happen is if I integrate this from 1 to 5, it should give me the same number. So I'm going to go to Menu, Analyze Graph, Integral. Integrate the red function now from 1 to 5. And notice we have the exact same number. Okay. Would have been the same if I had instead graphed just the 1 over x and then divided the result by 2. If I integrated the 1 over x, it would have been like 1.6 something, and then divide it by 2 makes it the 0.8. I think I have one more problem. If you want to try it on your own, you can. It's a pretty tricky one. It's one of those where you have to kind of think about the powers. But if you want to try it and then come back, we can try it together. All right, let's give it a shot. So we got x over 1 plus x to the 4th dx. So the problem here, I think it's really tempting to say, looks new color, that's fine. It's really tempting to say u should be 1 plus x to the 4th. But here's the problem with 1 plus x to the 4th. Then du would be 4x cubed. What's the problem with that, dx? I don't have an x cubed, and I can't create it. You can't create x's. You can create constants, but you can't create x's. X, just up here, what would that be the derivative of? That'd be the derivative of some kind of x squared, right? So let's just try making u x squared. Let's just see what happens. Just trust me on this. Follow me on this journey. So if u is x squared, that would mean, so this didn't work. That would mean that du is 2x dx. Well, I have the x. Can I create the 2? Absolutely. Throw that 2 out front, 1/2 out front then to cancel it out. So what do we have now? We have 1/2 integral. We have to change these to u's. So u of 0 would be 0 squared, which is still 0. U of 1, oh, how exciting. Still 1. So we're still integrating 0 to 1. We changed to u values, but it's still 0 to 1. 2x dx becomes my du. So I'm just going to put that on the top. We have du. Then on the bottom, u is x squared. Well, x to the 4th. X to the 4th is x squared squared. So this is 1 plus u squared. Du we already have there. So antiderivative of 1 over 1 plus x squared, or in this case 1 over 1 plus u squared, that's tangent inverse. So we have 1/2 tangent inverse of x evaluated from 0 to 1. U, tangent inverse of u. So at this point you could put the x squared back in there, and you could do it x equals 0 to x equals 1, but you're going to have to do the same thing. So we have 1/2 tan inverse of 1 minus tan inverse of 0. That's 1/2 times. Tangent is 1 at pi over 4. Tangent is 0 at 0, so this is pi over 8. Voila. That's all there is to it. All right, that was a lot. U sub is really useful. We use it all the time. And it's one of those things that I just kind of expect you to have in the back of your memory for any time that we're evaluating an antiderivative, any kind of indefinite integral. You should be able to think, maybe we should be using substitution on this. And sometimes it works, sometimes it doesn't, but the more you do, the more you get to realize that this is going to be a U sub problem or this is not. So make sure you try the worksheet, do the homework problems, and you'll be in good shape going into our second day of U substitution, where we're going to try what's called back substitution. Love you guys. That's why I'm here. Have a great day.